Topic 6.4 Electric Capacitance. Definition of capacitance. Capacitance is the change in electric charge of a system corresponding to a unit change in its electric potential. Mathematically, we can write that down as follows, where Q is the change in electric charge, C is the capacitance of the system, V is the change in electric potential. SI units of capacitance is coulombs per volt or farad. Dimensions is m-1, L-2, T to the power 4. Parallel plate capacitor. If a parallel plate capacitor is connected across a battery like this, both plates will have equal magnitude of charge but in different types. This is the circuit symbol of capacitor. When epsilon is the permittivity of the medium between parallel plates, if epsilon naught is the permittivity of vacuum or air, the ratio of the epsilon to the epsilon naught, K, is called the dielectric constant of the material. Those quantities are related to each other as in this equation. There is an electric field intensity directed towards the negative plate from positive plate. Say the magnitude of that electric field intensity is E. If the gap between two parallel plates is X and the potential difference is V, then E equals V by X. That is because electric field intensity is equal to the potential gradient. If the capacitance is C and the magnitude of charge is Q, we can write C equals Q by V. If the surface charge density is sigma, we can write Q equals sigma A. Furthermore, as per previously derived relationship, E equals sigma over epsilon. Capacitance of a spherical conductor. If the charge on a spherical conductor is Q and the radius of the sphere is R, then we can write the following relationship. Combination of capacitors. Series combination. When connected in series, all the capacitors have the same charge and the potential difference across the combination is the sum of the potential differences across each. Applying Q equals CV for the equivalent, by symmetry, we can write down the following relationships. Combination of capacitors when they are connected in series. This relationship is analytical to the relationship of resistors when they are connected in parallel. Parallel combination. When connected in parallel, all the capacitors have the same potential difference across them, and the amount of charge of the combination is the sum of the amount of charge in each. For the equivalent capacitor, applying Q equals CV, we can write as follows. This relationship is analytical to the relationship for resistors when they are connected in series. Energy stored in a charged capacitor. Work done in sending charge against potential difference during the charging process of a capacitor is stored as electrostatic potential energy and is thus related to the charge Q and potential difference V between the capacitor plates. A charged capacitor stores energy in the electric field between its plates. As the capacitor is being charged, the electric field and the potential difference builds up. That building up as shown in the following graph. There is a linear relationship between potential difference and charge. Since V equals 0 at the beginning of the charging process, as per the equation W equals QV, W also equals 0 at the beginning of the charging process. Say potential difference is V at the end of the charging process, then as per the relationship W equals QV, total work done during the process is given by average of initial value and final value. Distribution of charges on conductors having different shapes can be shown as in following figures. In an irregularly shaped conductor, more charges will be distributed in areas where the surface curves more sharply. In uniform shapes, charges will be distributed uniformly. The charge distribution on the surfaces of lightning rods will be as this. Corona discharge or point discharge. A corona discharge is an electrical discharge caused by the ionization of a fluid such as air surrounding a conductor carrying a high voltage electricity. It represents a local region where the air or any other fluid has undergone electrical breakdown and become conductive, allowing charge to continuously leak off the conductor into the air. The corona occurs at locations where the strength of the electric field, that is the potential gradient around a conductor, exceeds the dielectric strength of the air. It is often seen as a bluish glow in the air adjacent to pointed metal conductors carrying high voltages, and emits light by the same property as a gas discharge lamp. If a charged object has a sharp point, the electric field strength around that point will be much higher than elsewhere. Air near the electrode can become ionized, that is partially conductive, while regions more distant do not. When the air near the point becomes conductive, it has the effect of increasing the apparent size of the conductor. Since the new conductive region is less sharp, the ionization may not extend past this local region. In the atmosphere, trees and other grounded objects with points and protuberances may, in disturbed weather, be sources of point discharge current.